Hello everyone, so today we're going to be deriving an expression for the steady state absorption flux of a gas A into a liquid film thickness beyond which the concentration is around 0. So once it's absorbed in the liquid A and is consumed by a first order reaction with a reaction rate, species A has a concentration of CAI at the vapor-liquid interface and can be assured to be dilute in a solution such that diffusion can be described by Fick's diffusivity of one with no convective contribution. So to start off, we're going to kind of describe what we're looking at right here. So I'll draw like a little picture. So first we have this almost like cup, and in the middle we have liquid. And then on the outside, we have our gas. And then this distance right here is our film thickness that we're going to be working with. So I'll label that for us. So now let's get into the equations of like kind of what we're working with. So we have our molar flux of Na, and that is going to be equal to our diffusion coefficient of D, and then we will have our derivative of concentration A with respect to dz. Additionally, when we have our first order reaction rate of R, and so that's going to be important here. So we have negative R, and that's going to be equal to our thermal conductivity times our concentration of A. So the reason that this is negative is that because concentration flows from high concentration to low concentration, so that needs to be negative right now. So for our second order reaction rate, it will look more like this. I'll label this. And that will be equal to d squared Ca over dx squared minus Kca, and that's going to be equal to 0 because we are at a steady state, which is right here. We are at a steady state absorption, so it's going to be equal to 0. So to help simplify this, our K value here, we're going to set this equal to M over K over D. So we can input this back into our K value right over here, where we get d squared Ca over dx squared minus m squared Ca equal to 0. And the reason we can simplify this is because of that d value right there. We're going to assume that we're dividing this out. So I'll make that out for you so it's a little bit easier to understand. Okay, K over dCa. Then obviously it's just still 0 because 0 divided by d is still 0. So when we set that over here, we can actually simplify that to m squared Ca. So that's a little bit background in there. Sorry, I missed that earlier. So now while that's our general equation, we're going to make a more general equation so we're able to solve it with different kind of values going forward. So we have Ca of Z is equal to A cosine H mz plus B sine H mz. So this right here is our general equation we'll be working with here. So now we're going to be able to try to solve for different values here. So first, we're going to put that Ca is equal to 0. And this will actually, so if sine of 0 is 0, but cosine of 0 is 1. So if we set that equal to 0, we actually just get A. Additionally, if we set Ca equal to the Z is equal to our film thickness, we get A cosine of H m times the film thickness plus B sine H times m of the film thickness. So we have our three equations right here. One for B gives us the following equation of B is equal to a CA value times our cosine of H times our M film thickness over sine H M times our film thickness. We solve for C though. We get CA cosine of H times our M film thickness minus, again, CA cosine H M film thickness times our sine H of M film thickness times sine of H M over film thickness. So this simplifies down to, because these are fundamentally different terms, we can simplify this down to so we have the following equation right here, and this can be simplified down into CAI times so now we can exemplify our molar flux with our NA being equal to, setting it equal to 0, or Z value equal to 0, which is equal to our dCA over dZ, Z being equal to 0, which is equal to our diffusion coefficient times our concentration times our derivative of times our derivative concentration, which is equal to our cosine over film thickness times M times our sine of film thickness times M. So this is our following expression for our film thickness. This is our film thickness absorption rate. So thank you very much.